Okay, so welcome back. Now you're just got familiar with what is how to write a function that is to be executed on GPU, right? So don't worry, even if it is taking some time to grasp the things like global, what is global, what is what are these parameters in this triple angular brackets. We'll try to cover all these things one by one, right? As of now, what is expected from you? How to write a function to be executed on GPU, right? Function definition and function call. That's it, right? Even in function call, you're not expected to understand what is this, right? The next presentation, we are looking for what is thread organization in case of your CUDA. But before that, I'll just quickly walk you through what is how to compile this code. So we have used this complete, let's say, command to compile your code. So first is referred as NVCC, that stands for NVIDIA CUDA compiler. Just like your if you run or compile C program, we use a GCC compiler in Linux, right? Or maybe Intel compiler is there. Similarly, to compile a CUDA program, we use NVCC, that stands for NVIDIA CUDA compiler, right? This is specific to architecture, which type of GPU architecture you are using, and based on that, you can mention this command. As of now, you just use as it is. Assume that we are having this type of architecture, and you are you'll be using only this particular specific command, right? Next one is here another flag we are using -o, that stands for once compilation an output file will be generated, right? That is object file we consider in different programming languages. Here output file we consider, and we are assigning name that output file as out. You can assign any name, whatever you want, right? And finally, here we are mentioning which program you want to compile using this NVIDIA CUDA compiler. So this is the program name, right? Output file will be created and it will be named as output on this architecture. And once output file is created, we are going to use -run command to execute that executable file, right? So this is how we use compile and run the accelerated CUDA code. Fine. I hope there is no doubt till this point. Even if you have any query, you can drop in this chat box. Fine. Now, next thing we are trying to understand the most important topic, that is CUDA thread hierarchy. No matter whether you follow the Python-based CUDA programming or C++-based CUDA programming, this is the most important topic, that is CUDA thread hierarchy, right? You are supposed to understand this concept, right? Otherwise, you will not be able to solve any assignment, maybe the certification assignment also. This is the most important topic from entire course, that is CUDA thread hierarchy. For that, I will present my presentation because there are some topics not clear in the presentation that is made available in this Jupyter notebook. So I'll refer my presentation with some exercise problem so that we'll get clear idea about what is the thread organization in case of CUDA programming. So those who are familiar with C programming, these are the typical steps we follow, right? So no matter which program you are writing, we follow these things. Like first of all, we will include some libraries, declare variables, then allocate memory to those variables, initialize those variables, perform computation, store the results, and free variables, right? So whatever program you write, any computation, we follow these steps. Maybe you are performing any assignment related to a data structure programming, or maybe some any other real world problem you are solving using C programming. First of all, you include some desired libraries, and that is common for all the programming language. First of all, you are supposed to include some libraries. Then for your computation, you declare some variables to store the data, right? Then you allocate memory to those variables, initialize, perform computation, and finally store the results. And once you are done with all use of these variables, maybe if you allocate memory dynamically, you are going to free those variables, right? Now, as I told you, GPU is going to perform only computationally intensive tasks. Not all tasks from your C program is to be deployed on GPU. Only the required topics or only the required computations will be diverted towards the GPU. And what are the required computation? The tasks which are very computationally intensive, right? Now here, as I told you, GPU is a coprocessor which is going to transfer only computationally intensive jobs to the GPU, and GPU will perform all those computations in parallel with thousands of cores available in it, and after the computation, results will be given back to the CPU, right? Now, these are the steps that we have to follow when you write a CUDA program, and that is common for your C++ application or maybe Python based CUDA application, right? Only the things are going to be syntactically different, how we are going to perform all those steps. Every step is numbered here, so you can follow here. So first thing, you have to declare CPU variables, right? Before we go for these steps, remember that we are having CPU which is having its own memory and GPU which is having its own memory, right? Your program execution start on the CPU side, and only computationally intensive jobs will be given to the GPU, and GPU will perform this operation in parallel, and results will be given back to the CPU, right? So a typical GPU program, how it looks: declare CPU variables first, because first the CPU is the initiator. So first of all, we have to declare all the variables and memory on the CPU side first. Allocate memory to the CPU variables, that is the second step. Third step is declare GPU variables, right? Then allocate memory to the GPU variables, initialize data on CPU, copy data from CPU memory to GPU memory, and instruct CPU to perform execution in parallel and copy back results from the GPU to CPU. So how it is happening? Let's take a simple example. You want to perform matrix multiplication on GPU. So what will you do first? First of all, you declare all the matrices on CPU memory. You will allocate memory for those matrices on CPU side, right? You initialize values on CPU side. Now your matrices are initialized and that are present in the CPU memory. But problem is that you want to perform that matrix multiplication on the GPU side, right? Now data is present on the CPU side. For that, first of all, you have to transfer those matrices from CPU memory to GPU memory, because the computation is supposed to happen on the GPU. So we'll transfer this complete matrices on GPU memory. But before transferring, first of all, we have to declare GPU variables, because anyhow, when GPU is going to perform computation on those matrices, GPU is going to refer some names. So we have to declare some variables for those matrices. But now on GPU side. Now once you declare those variables, then allocate memory on the GPU for those matrices, right? Based on their corresponding size, maybe 1000 cross 1000 or 5000 cross 5000, whatever is the size of matrix. According to that, we have to allocate memory on the GPU side, right? Now CPU is having matrices with the data initialized. Now GPU, where we have allocated memory only. Now the matrices that are initialized on CPU memory will be transferred from CPU main memory to GPU main memory, right? Then CPU will instruct using those functions that we mentioned using global keyword, right? So this function will tell GPU that we are supposed to execute this computation in parallel on GPU, right? So the CPU provide those instructions in terms of function call to GPU for parallel execution. Now GPU will perform all those operations in parallel, whatever matrix multiplication is there, and results will be again stored into the GPU memory, and those results will be again copied back to the CPU side, because we want result at the CPU side, right? So results will be copied back from GPU memory to CPU memory. Fine. So this is the template that is very common to any sort of program you try to write it on the GPU. Whether you use C++ application or maybe Python, you have to follow the same strategy. So maybe you take few minutes to read step by step what are the 8 steps mentioned here, right? No matter in Python also you have to follow the same steps, right? Only syntax will be different over there, right? So take 1 or 2 minutes, read these steps, and if you have any doubt in this case, you can ask. Yes, any doubt? Okay, so this is the way we try to execute and compile your CUDA program. So extension will be .cu, that indicates CUDA program. We use NVCC compiler and will execute the whatever output file will be generated. So in your cloud platform, you don't have to write explicit execute command. So entire command is already provided. Now the most important thing in CUDA programming is thread organization, right? So here thread is the basic execution. Just a second, there is a question, I guess. Can we run GPU based coded codes in command only or any normal interpreter? Typically, you can use command line based execution, right, for compiling and executing these CUDA codes, right, from terminal. But now they have provided this cloud environment, so all the commands and everything they are already mentioned in the cells. We just need to execute those. If you install CUDA in your local system, and if you want to compile and execute, then first of all CUDA toolkit you have to install. Then using NVCC compiler, right? The simple steps you have to follow, like NVCC compiler followed by that file name, and if you want to specify architecture name, likewise you can specify, and one output file will be generated. If by default the output file name will be a.out, and to execute that we can use ./a.out. That is if you are having local system, right? In case of your Jupyter notebook, the command is already mentioned in the cell. You just have to run those commands. Fine. Can we submit executed files from local system? That is fine, but in your local system may not be having a very powerful GPU, right? Like T4 GPU that is present in your cloud system. If you have local system where GPU is more powerful, then you can utilize that also, right? But if you're talking about the submission for this particular certification, so where you don't have to write complete code or something, only few instructions will be mentioned in the code where you have to modify it, and immediately you have to run in the Jupyter notebook itself, and automatically it will be evaluated and will get certification. So for certification point of view, you just have to limit to the instruction mentioned in the certification. If you're willing to work on the assignment problems in the coding round, in that case you may use your local system also, or maybe we will provide that a cloud system, right? If you have GPU powerful enough with you, then you can use that also. Fine. Okay, now the thread organization is very important, and for that we will try to understand with the simple example, that is vector addition, right? So vector addition means we'll be having two arrays. We have to perform addition of those array elements, right? Let's say we are having array A, B, and C. So array A and B are added together to get array C, and we are going to add corresponding array elements. For example, like this. So we let's say array is initialized to 2 and B is also initialized to 2. Now we have to perform array A plus array B, then corresponding element wise addition to be performed, right? If you consider it as a sequential execution only using single thread, how it looks? First of all, we will perform when I equal to 0, we'll perform A of 0 plus B of 0 equal to C of 0. Then next one is I equal to 1, then A of 1 plus B of 1 equal to C of 1. You can see accordingly the vector C is getting updated, and likewise we'll perform step by step every addition from 0 to 7. So array size is 8 and index is from 0 to 7. So step by step we'll perform this addition 0, 1, 2, 3, 4, 5, 6, 7 based on this I value, right? So this is how sequential execution happens using single thread. But if suppose in parallel execution I'm having 8 threads are there, and that can be executed on 8 number of cores available, right? So 8 cores are available. I can create 8 number of threads and I can assign every thread different task. For example, here the array size is 8 and I can launch 8 number of threads. Those are indexed from 0 to 7, right? For every thread we'll be having unique ID 0, 1, 2, 3 likewise, right? And every thread is going to perform a different task, right? For example, thread 0 is performing array of 0 plus A of 0 plus B of 0 and is storing in C of 0. Similarly, let's say thread number 4 here, which is performing A of 4 plus B of 4 equal to C of 4, right? So likewise, if I'm having 8 number of threads, right, I can launch 8 threads that can perform operation on 8 independent elements of this array, right? And you can get a solution in the single shot. Now, if you recall that video where the paintball was painting the smiley step by step, one paintball at a time, that is this type of computation. So first of all, it will execute thread numbers, work on A of 0, B of 0, then index 1, index 2, 3, 4, 5, 6, 7 likewise. So step by step it will happen, because in sequential execution we'll be having only single core to perform all these operations, right? And the single core is capable of computing one operation at a time, right? That's why it will take 8 number of steps to complete this operation. So just like your that paintball who is painting that particular smiley by using throwing one paintball at a time. And this is like your that Mona Lisa painting machine, where all the painting that pipes are throwing those paintballs at the same time. Same thing is happening here, right? Here all threads are there, 8 number of threads, and all 8 number of threads are working on different index values, and they will be performing operation at the same time, right? So in the one attempt itself, all the 8 computations will be performed, right? So this is called as parallel execution using 8 number of threads. Getting it? Yes, any doubt? Okay. Now let's try to understand how actually these CUDA threads are organized. Very important topic. If you understand this, I can assure you most of the problem statement will be able to solve very easily, right? But if your concept of this thread organization is not clear, then it is very difficult for to imagine how you are going to solve any problem, right? So pay attention. Even if you have any query, even a very small doubt is also there, then try to clarify during the session itself rather than waiting till end of the session or maybe discussion on the WhatsApp, right? If you ask question during the session, I can explain maybe with some example, but if you ask in the chat box after the session, then it is very difficult for me to describe using the only text information, right? Okay, there is a question, normally how many threads can be organized by dual core processor? I guess you are talking about CPU side now. So you can launch any number of threads, right? That means as long as you're satisfying the maximum integer number in your system, right? So you can launch maybe 10 number of threads on 2 cores also, or maybe 100 number of threads. But we are having 2 number of cores, that means only 2 threads can be executed in parallel, right? So if I'm having, let's say, 10 threads launched, and if I'm having 2 cores, so all the 10 threads will continue execution, complete execution in the lot of 2 threads at a time, right? Because hardware we are having only 2 cores, so maximum threads that can execute in parallel will be 2 only. You can launch multiple threads more than 2, but at a time only 2 number of threads will be scheduled on those cores. Yes, ideally we want threads equal to cores, right? Yes. If you are having octa-core machine, then you can consider launch 8 number of threads. Plus nowadays Intel also providing that concept of hyper threading, where they mentioned that if you are having 8 number of cores, maximum number of threads you are supposed to launch to get better performance is equal to 6. That means on single core also they are providing some overlapped optimization so that 2 threads can be logically executed on the same core at a time, right? That is concept is called as hyper threading, but that is not in the context of this CUDA programming. It comes under another programming language that is called as OpenMP. Yes, typically we can say that the number of cores equal to number of threads using in any time. Yes, ideally the best solution is if you are having, let's say, 100 cores, you launch maximum 100 number of threads, right? And you divide your task among 100 threads only. Ideally, I'm speaking, right? Okay. Now pay attention for this thread organization. Almost 50% of your job will be done if you understand this thread organization. Rest of the topics like memory management and all those things, those are not related to exact computation oriented, so that easily you can understand, right? But most important thing is this thread organization. Okay, now let's try to understand how these threads are organized in case of CUDA programming. You got now how to launch any CUDA programming kernel, right? You know how to write a function that to be executed on GPU. But now we are talking about that parameter that we mentioned while function calling in the angular triple angular brackets 1 comma 1. That is nothing but your thread configuration you are specifying to that function, right? And that thread configuration we'll try to understand now. So let's say we are having threads. Threads are grouped together to form a thread block, and thread blocks are grouped together to form a grid. So this is the hierarchy maintained in case of thread organization in CUDA, right? So some n number of threads are grouped together to form a thread block, and n number of thread blocks are grouped together to form a grid. So that is the hierarchy. So let's try to understand what is threads, blocks, and grid here. So here the example is given. So here we are having 4 number of threads are grouped together to form a block, right? So you can see here T0, T1, T2, T3, that stands for 4 number of threads. We have combined this 4 number of threads and we are going to consider it as a block, right? So first statement is threads are grouped together to form a thread block. So these are the 4 threads, they are grouped together to form a block 0, and these are the threads, 4 threads grouped together to form a block 1, right? So every block we are having 4 number of threads. Now next statement is thread blocks are grouped together to form a grid. So here 2 blocks are there, we are going to combine them and we are going to consider it as a grid, right? So how we can, in reverse order, how we can mention? We are having a grid which is having 2 blocks, and we are having a block which is having 4 threads, or 4 threads are grouped together to form a block, and 2 blocks are grouped together to form a grid. This is how your threads are organized in case of CUDA programming, right? Now these are the first two statements. Threads are grouped together to form a block, and blocks are grouped together to form a grid. Now every thread and thread block is going to have IDs, identifiers, right? So you can see here, I am referring these 4 threads with numbers 0, 1, 2, 3. So every thread inside a block starts with ID 0, right? So 0, 1, 2, 3. So these are the IDs for 4 threads inside this block, 0. And for block also, it is having its own ID, and that is also starting with 0, right? So let's say I'm referring to this thread. So how I can refer this? This is thread number 2 from block number 1. If I refer this thread T1, I'll say this is thread number 1 from block number 0, right? And we can retrieve all these identities, right, using the insider CUDA function, right? So how to retrieve that and what is important of that, we will see with some examples. But as of now, key takeaway from this slide is threads are grouped together to form a block, and blocks are grouped together to form a grid. Next statement is every thread is having ID, and every block is having also a unique ID. Fine. Now, one more important point to notice here is, you can see I'm having thread number 0 here also, and thread number 0 in block 1 also. Thread number 1 in block 0 also, thread number 1 block 1 also. So meaning is that the thread IDs are local to the block, right? And here also, the in case of block 1, thread IDs are local to the block. Fine. So here, now these are the 4 parameters that we can retrieve from each thread, right? Inside your GPU kernel, we can retrieve these values. For example, let's say you want to find out corresponding thread ID. So we'll be using the syntax or this thread idx.x, right? If you want to find out the ID of that particular thread, we'll be using thread idx.x. If you want to find out block ID of that particular block, then we'll use block idx.x, right? You want to find out number of threads per block, then we'll be using block dim.x. And if you want to find out number of blocks inside the grid, we'll use grid dim.x, right? So if you want to find out for this thread what is its ID, I'll be using thread idx.x. Let's say you want to find out this particular thread in which block it is there, then I will use block idx.x, right? Now let's say I want to find out number of threads in this particular block, right? It is 4, so I will use block dim.x. This will give you number of threads in that block. And number of blocks I want to find out, then I'll use grid dim.x. For example, here we are having, these are the 2 blocks where thread IDs are there, and these thread IDs are local, right? Block indices are there, that will also start with 0, right? There are 2 blocks. Then each block has 4 threads. I can use retrieve that information from using block dimension.x. And finally, we'll be having grid dim.x, which will give you total number of blocks inside the grid. Fine. So these are the 4 parameters, very important to complete your exercise problems in the certification, as well as to attempt the coding round. So again, take few minutes, you go try to understand what is thread ID, what is block ID, local block ID, local thread ID, right? How they are organized. And if you have any question, you can ask. Okay, there is a question. If I want to access a thread, let's say thread T2 from block 1, how can I access it? Very good question. That is our next topic that we are going to discuss. As of now, you just keep in mind how threads are organized, how blocks are organized, how we are going to assign thread IDs, how we are going to assign block IDs, what is grid, block dimension.x. So you just understand this, we'll get all those things in detail with some examples. Any other doubt? Okay. Now, this part, I will not explain why we are using this dot text, because here we are organizing threads in only one dimension, right? So in only X direction, we are increasing the threads. But when you will work on the data structures like matrix or two-dimensional, three-dimensional array, then we can arrange the threads in 2D or 3D also, right? But as of now, we'll limit ourselves to get concept clear from one dimensional only. Once we'll get comfortable with this one dimension organization, then we'll move for the two dimension, right? And that is the reason we are having dot x, dot x, dot x at the every parameter here. Meaning is that thread ID in the x direction, block ID in x direction, block dimension in x direction, grid dim in x direction. That's it, right? So the x indicates in x dimension. If you are having y, that indicates in y dimension, right? If you are having matrix related computation, then we'll be using two-dimensional thread organization. Likewise, fine. Now let's try to use this, understand this simple program from your Jupyter notebook, right? Okay. So here there is a program that is called as first parallel.cu, right? And what we have to do, we have to refactor this call to first parallel to execute in parallel on GPU, right? So what is the first step? First step is you have to write global keyword so that compiler will understand this function is supposed to be executed on GPU. Next thing is we have to provide here configuration, right? Here what we provide, number of blocks, comma, number of threads, right? So you can see here we have to pass in this angular curly bracket, angular brackets, triple brackets. First parameter will be number of blocks and number of threads per block, right? If you see in this presentation, what I said here, I'm having two blocks and every block are having four threads. So total number of how many threads we are having? 8 number of threads, and they are organized in blocks of size 4, right? So same thing we have to mention here, how many, indirectly we are saying how many threads you want to launch to perform that particular computation. Here, as of now, I will mention 1 comma 1. Meaning is that we want one block and every block is having one thread, right? And next thing is we have to mention here CUDA device synchronize, right? I will just copy paste here CUDA device synchronize. Now you save this program, right? And now I'll come back here where we are executing this first parallel.cu, right? I will execute it and you will see that this should be running in parallel. That message is getting printed here from this function. As of now, we just created one thread only, one block, and every block is having one thread. Now, let's say I will change this to 2. Now you tell me how many times this printf will get printed? This statement gets printed how many times? Two times, right? So how many, you just do the computation, how many threads you are creating, right? I'm saying two blocks and every block will have one thread. So total number of threads will be two, exactly. Each block have one thread and we are having two such blocks, right? So two threads will be created, right? And two threads are there, and when you execute this function, automatically two threads will execute whatever code that is mentioned in this function, right? So you imagine that here, once you are calling this first parallel function on GPU, two threads will be created according to this configuration, and whatever code is mentioned inside that, right? This code will be executed by the two threads. Again, we are not doing any important computation here. We are just trying to understand this thread organization. Fine. Now, let's execute and confirm whether it is happening. Yes, two times it is getting printed. Now again I'll play around with, I'll change 1 and 2. Now you tell me how many times the same statement gets printed. Again, it is going to be 2 because we are having one block and one block is having two threads now, right? So two threads are there and two threads will print this statement, right? Again, let's execute and we'll confirm. Fine. Now I'll change 2 comma 3. Now how many times it will get printed? Exactly, 6 times, right? So we'll be having two blocks and each block will be having three threads, right? So let's run this, right? So it is getting printed 3 times, right? But obviously it is not a very important kind of computation, right? Same thing is getting executed by every thread, right? So it is not an ideal parallel code. Yes, just to answer to that, it will be number of blocks multiplied by number of threads per block to be specific, right? Now you got how threads are organized. Now you do one thing, you play around with and you give any number to that and check whether for all numbers it is working or not. And you tell me if you face any error. Modify code here, you go back and try to execute. Modify again here, save it, go back and execute. Let me give any very big number as number of blocks. Let's try to execute. Yes. Any observation? Right observation. Right. When Karthik, I guess, can be exceed integer limit as well, right? So here there is for every specific GPU, there will be limitation on number of blocks, number of threads, or number of threads per block, right? So for every, it is not like that we can have any number of infinite number of threads we can launch, right? So there will be one specific device query code that will be present in your CUDA toolkit, which will tell you how many number of threads per block you can launch. Specifically, in this particular GPU, I guess it will allow you to launch maximum 1024 threads per block. Right? I think it will allow you 1024 threads per block. Right? Yes, so you'll get some error that you cannot give tool that value too large, right? So it is not like that any number of threads you can launch. So whenever you are writing any parallel code, if let's say your data size is very huge, let's say in billions of data points, so you cannot launch billions of, let's say, threads. So first of all, you have to find out how many number of threads are allowed to launch, right? Now we have limitation of number of threads in case with respect to a specific GPU architecture, and according to that, now you have to distribute work among multiple threads, right? So the limit will be specific to a specific GPU. For example, now we are referring NVIDIA T4 GPU, right? Maybe if you refer Ampere, the one Ampere GPU, Ampere architecture, maybe you'll be having the different limits, right? If you go to very small GPU like in laptop, maybe which is having different limitation threshold values, right? So every time you have to check how many threads are practically allowed in your on your GPU. Then you can decide the maximum number, right? So that is second observation from this thread. But typically, the problem statement that you are going to work in the coding round as well as in this exercise problem, where you have to just ensure that you are not going to cross this 1024 in the number of threads per block. You can launch maybe 10 or hundreds of these thread blocks, but maintain the block size will be always less than 1024. Fine, that is a key takeaway from this. Now, you know this block ID in block indices and everything. Now you just read this statement, thread and block indices, right? And we'll go to the next exercise, that is use specific thread and block indices, right? 1 minute, you just read these statements. Right now, we have the next problem is using this specific thread and block indices. Yes, Subhradip, I guess you're asking the right question. Is there only one grid? Yes, we are having only one grid here, right? If you open this code now, thread and block IDX. So what is there in this particular block? So we are assigning specific task to specific thread. For example, if thread ID is 1023, from block 255 if that thread only will print success message, right? Or else all threads will print failure message, right? That means here for specific thread from specific block, we are assigning some task, right? Now, what we have to do in this exercise, we have to update the execution configuration so that the kernel will print success message. Now, how will you give this execution configuration? As of now, it is having one block and one thread per block. So only one thread is there. Now you have to modify this configuration so that this print success message will be printed. Yes, Anuja Jadhav, I guess. Yes, you are right. Right. So what you are doing here, if you see this statement, it is this success is printed by the thread ID 1023 and block ID is 255. That means you must have at least 256 blocks, right? 256 block, and you must have at least 1024 threads per block, right? Though we are having this 255, I am saying 1023, but your thread index starting with 0, right? So in that case, we'll be having, this is the last thread, though it is 1023, but the index is starting with 0, so total number of threads will be 1024. In case of block ID, also same thing, block ID starts with 0, so total number of blocks will be 256, right? So 256 will be here and 1024 will be here, right? Again, if you're not getting immediate solution, I think here the solution link is there, so anytime you can check this, right? And obviously here, if you see, else message is also there, but if you keep this else message as it is, what will happen? All the rest of the threads from rest of the blocks will print this failure message, but what is expected, only success message is required, so you just have to remove this else component, right? And now you modified this state configuration and this program also, so you can go back and compile and execute, and you will see, sorry, yeah, what is missing from this program? What is the error? Why I'm not getting answer here printed? Exactly. So we missed synchronization, right? Good. So here I'll execute one more time and you see the success message will be printed. Right, absolutely right. Yeah, and most of the time, because if there is a compilation error is there, syntactical is there, error is there, you will find out that error, right? But these kind of errors, right, it will not encounter any error message or something, directly it will execute and you will not be able to find out what is happening actually. You'll see that I'm doing all those things correctly, but somehow the output is not getting printed, right? So these kind of let's say problems are very difficult to debug, right? So always ensure that whenever you are not getting output message, first thing is you check whether after CUDA call whether your function is getting terminated or not, right? Whether it is synchronized or not. Anyway, so I hope it is clear till this point, but till this point we did very useless computation because we're not doing any productive work in this parallel environment. Uh, is there any alternative method for synchronize? I'm not getting what do you mean by alternative method. If let's say we are having any other CPU function is there after this, then maybe it will execute another CPU function. But provided that you want to execute that CPU function in parallel with this GPU function. So now GPU also executing same time on CPU, that CPU function will be executing, right? But problem is that after this CUDA device synchronization, immediately your complete program is terminating. So that's why whatever progress is there with this GPU function will be lost and your program will be terminated. Fine. So now next is, till this point we just did some dummy computations or dummy message we tried to print just to understand your thread and block configuration, right? Those who got this thread and block configuration as of now, you can assume that 30 to 40% of your work is done, right? Understanding this CUDA programming. That is the most crucial part, right? Now, till this point, we did only dummy computations. We can go for now accelerating the loops, right? So take again couple of minutes, read this statement, what is happening, and then we'll go to the exercise again. Can we use multiple times? Yes, if you are, let's say, having multiple codes, right? Multiple GPU, for example, here one function is there, right? After that, let's say another one function is there, right? Like, sorry, I'll just name them randomly. Let's say one function, this is second function, this is third function, right? In this case, now what happens? Let's say you want to ensure that this GPU computation should not start before the completion of this GPU function. Then in that case, you have to ensure that there is a device synchronization between these two GPU calls, right? Maybe again you want to ensure that first complete this GPU computation, right? And then only you can go for the next GPU computation. In that case, you can use device synchronize. But if I don't use this, let's say, what will happen, right? If I don't use this, now what will happen? For this same program, I have to write definitions for all these programs. Okay. Right, 4 times you are getting success. If I remove these synchronizations, right? No. So that is why synchronization is required. Now here we are calling same function, right? We are calling same function, but let's say we are having one function is here, we are having different function is there. For example, let's say output of this function is input to next function. In that case, we cannot, if you don't use this CUDA device synchronize, CPU will launch this function, and before this function completes, CPU will launch different GPU function, next GPU function, right? But output of this GPU function is input to next GPU function here. So in that case, we have to ensure that this CUDA device synchronize, so that first this will complete and then it will start only, right? Right. It was quite good question. Okay. Fine. Now we got specific threads and block. Now let's try to understand this accelerating the for loops, right? Till this point, we just did only dummy computation. You just read these statements. Now what we have to do, let me open this first. Refactor loop to CUDA kernel, new kernel should put only one iteration. Okay. Now we have given here loop function. First of all, we have to launch as a kernel. Kernel means GPU function, right? So CPU function and GPU function, rather than they use names as a CPU function and kernel. So whenever I'm referring kernel, means that is a GPU function, right? Be sure to use execution configuration to control how many iterations to program, right? First of all, it is asked to modify this loop function to be executed on GPU. What will be your first step? Immediately you apply global keyword before that function definition, right? We use this global keyword now. Next thing is we have to mention the configuration, thread and block configuration, right? Here I will mention, let's say 1,1, right? And next step will be CUDA device synchronize, right? So let's go back and run first. Okay, somewhere I did mistake. Now you can see it is printing iteration number 0, iteration number 1, 10, likewise. Now you observe this code and tell me what is wrong with this code. Yes, only one thread is there. But let's say you go on increase number of, let's say 10 threads equal to 10. Now you tell me what is wrong in this code. Yes, you're right, Subradweep. Then Venkata, Karthik also you are using the, you're right. Exactly, right? Almost all of you are correct here. You can see here, though we are launching 10 number of threads, but each thread is going to perform the same thing, right? So if I execute this code, what we are expecting? Only 9 iteration to be printed. Now every thread is going to repeat the same thing, right? So thread 0, thread 1, thread 2 10 times, thread iteration is 10 times, 9 iteration number is 10 times. So we are doing useless computation here. We have created 10 number of threads to print this matches 10 times, but unfortunately we have not modified this code that is inside this function. Now can you modify this code? I will just modify this code, and instead of this percentage %di, I will mention here thread idx.x, right? And now if I execute this, you'll see the iterations will be printed only 10 times. And now if you want to find out which iteration is printed by which particular thread, you can use this thread idx.x, right? So this is iteration number 0 will be written by thread 0, 1 is written by thread 1, 2 is written by thread 2, and so on, right? Getting it? Now let's say I will change this 2, 5. Now you tell me what will be the output here. Exactly. Thread idx.x will give you only local IDs. Look, what happens when you call this loop function with this thread configuration, number of threads will be created according to their block size and number of blocks, right? Whatever you are mentioning inside this, that will be executed by 10 threads, right? And all these 10 threads will perform, you execute the statement that are present in the your function body. So my question is, if I modify this configuration as 2 comma 5, what will be the answer here? What will be the output? Right, so you can see here thread idx.x is local to the block, right? So thread idx.x means thread 0, 1, 2, 3. These are local to the block, right? And how many blocks we are launching? 2 blocks, where every thread block is having 5 threads numbered from 0 to 4. So 0 to 4 in block 0, 0 to 4 in block 1. So first of all, block 0 will maybe execute all the threads, then block 1 will execute all the threads, or maybe all will be executed at the same time, right? Now if I execute this, we will get 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Why this is happening? Because we have 5 threads per block. Now you tell me, how will you modify this particular statement here, thread idx.x, so that we'll get message as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You have to modify. I will give you clue as you can use make help of block idx.x, comma, block dim.x, comma, thread idx.x. So you can use these 3 maybe values, so that you can create a formula using this all these things, right? You can mention that formula here, so that with the same configuration you will get message as 0, 1, 2, 3 till 9. Think on it. You think on it. Meanwhile, let's try to print this message, thread id and block id, because we created 2 blocks, 5 threads. So we are supposed to get how many messages? 10 messages, 5 from each block. So let's execute. We'll get configuration, that is thread 0 block 0, thread 1 block 0, thread 2 block 0. Likewise, in block 0 we are having 4 threads, in block 1 we are having 5 threads, right? Their corresponding IDs are there, right? And again, it is not mandatory that this sequence need to be followed. Block 0 first, then block 1. Thread 0 first and thread 1. Because all threads are running in parallel, so we cannot assure that which thread gets executed is going to print first. All threads will be executed in any order, right? So don't get confused that make assumption that we are getting in order means block 0 will get executed first, then block 1. It is they are just printing in this sequence, not they are executed in one after another. Fine. Okay, so now you can modify this. If I make this 5 blocks and 2 threads per block, then you can see here this is the configuration. So in every block we are having 2 threads. So block 0 is here, block 1 is here, right? Then block 2 is here, block 3. If you execute in your machine, maybe you will get different order here, because all of them are executing in parallel. Or maybe let's run one more time so that order will be changed, right? So you can see order is going to change here, right? So all threads will execute in parallel. You play around this by changing this thread and block configuration, and try to first of all hypothesize what will be the output, right? You just imagine what will be the output, right? And then you come back and execute and check whether you are getting the similar output or not. Fine. No, don't worry if you're not able to get that exact formula, right, using these parameters. So let's try to understand what is the importance of this. Let's say here you have given data to work on, let's say 8 data points are there, right? And obviously data is indexed from 0, like your threads are indexed from 0, right? Now on GPU, you have to perform some operation on this data, right? So 8 data points are there, and you decide that the configuration will be 2 blocks, and every block will be having 4 threads, right? So 2 blocks and 4 threads here. Now, what is ideally you are expecting? So thread 0 will work on, from thread 0 from block 0 will work on this data number 0, right? Thread 1 from block 0 will work on data number 1, and so on, right? So thread 0 from block number 1 will work on data 4. Thread 1 from block 1 will work on data number 5, and so on, right? This is what ideally we want to map your threads to work on the data points. But if you see, your block dimension is 4 here, that means 4 threads per block, right? Your block ID is 0 and 1, right? And then we are having thread IDs, those are local to these threads, right? And now if I say here, just a second, if I use directly thread IDX value, right? So if I say data of thread IDX dot 0, which will directly work on 0, right? This is the 1, so it will work on 1. This ID is 2, so it will work on data 2, and this is 3, so it will work on 3. But problem is that in block number 1 also we are having thread 0, right? So if block 1 is working on this thread idx.x, using this thread idx.x, it will also try to modify data on 0. Ideally what we were expecting, this thread 0 from block 1 to work on data number 4. But if you follow this data, if you follow this thread ID, then it will work on again same data, right? Both the blocks will work on the same data. So same thing was happening in your this case also. If you if you use this, right? So if you use this configuration 5,2, it is to print iteration number 0 to 5 and 0 to, the configuration is 5,2, 2,5 will do. It used to print 0 to 5, 0 to 4, 0 to 4. But what we were expecting 0 to 9, right? So that is called as global ID. So here we are having local IDs, thread 0, right? Thread 0 to 4, these are the local IDs, 0 to 3. Now we have to convert these thread IDs into global IDs. Global IDs means this will be the thread 0, 1, 2, 3, and this thread is supposed to get ID as 4, then 5, 6, and 7, right? And for that we can use the simple formula like this: thread idx.x plus block idx.x multiplied by block dim.x. Let me check anyone got the solution or not. Yes, Janaki Meena ma'am, you got the correct answer. So when we're retrieving particular thread value, we must mention its block. No need to mention because we are not retrieving using block and thread ID, right? By specifying two parameters. We are going to use this formula so that whenever we are having this ID equal to, let's say 4, that means we are referring this, right? Now let's try to understand how this particular thread's global ID gets value equal to 4. So we'll be having this formula thread IDX dot x plus block IDX dot x multiplied by block dim dot x. Now block dim is going to be constant because when we are mentioning two blocks with 4 threads each, so all blocks will be having 4 threads. So that's why 4 is constant. Now let's say we are referring thread number 0. It is a local ID. Now we are to calculate is global ID. So how we are going to calculate using this formula. So we just have to mention here thread ID, that is local, and block ID. So for this thread, its ID is 0 and its block ID is also 0. So 0 plus 0 multiplied by 4, it will be 0. So this thread number 0 from block number 0 will be mapped to data number 0. Next, thread number 1. Here thread number 1, its block ID is 0. So what will be the answer? 1 plus 0 into 4, it will be 1. So this thread number 1 from block number 1, so from block number 0 will be mapped to data number 1. Right? Next thread 2. Block ID 0 multiplied by 4, 0 plus 2, it will be 2. So it will be mapped to 2. And same with the thread number 3. Now if you see this thread number, what we are expecting, this thread number is supposed to map to data number 4. Right? Now if you put for this thread the values in this formula, right? So you can see here for this thread number 0, block ID is 1. So block ID is 1. So 1 multiplied by 4 plus 0, it will be 4. So it will be mapping to 4. Now for this thread 1, block ID is 1 multiplied by 4. So it will be plus 1, it will be 5. Right? And likewise. So you can see here, using this formula, we can get global IDs. Right? So those were the local IDs 0, 1, 2, 3, 0, 1, 2, 3. But now we are getting global IDs 0 to 7. And now if I use this formula in your code, here thread IDX dot x plus block IDX dot x multiplied by block dim dot x. If I use this now and execute the above program, we'll see the IDs are from 0 to 9. Right? Now I have assigned every thread an independent task or different task here. Earlier, if you don't use, then all these threads from block number 1 will also be mapping to data 0 to 4. Fine. Again, take few seconds, observe it, play around it. If you have any query, you can ask. We'll be having further 10 minutes break here. Right? So meanwhile, you can have the tea break or coffee break for 10 minutes, and then we will continue with this next topic. Right? Meanwhile, if you have any questions, you can ask, we can discuss here. Those who want to take break, tea break or coffee break, you can join at 4:10. Okay, so when we retrieving particular thread value, we must mention it with its block. No, so we just get exact value only with the thread values without the block ID. I'm not getting your question. Can you start your mic and ask?
Sir, can you hear my voice? Sir?
Yes, your voice is clear.
Sir, we save the value in each thread as a unique value, sir. In the first block,
Yes.
we can save the value as 2 in the thread 0. And we
No,
can
we are
save
not.
the another particular value in the thread 0 in the second block. If only I get the retrieve the value only along with the thread ID as 0 and mention it at block 1. Can we do that
Okay, I'll just.
without entering the block ID? Can we retrieve the exact value only with the thread ID, sir?
If you use only thread IDX.x, it will always give you.
Here we mentioned
local
the thread ID and the block ID to retrieve the unique value.
here.
Because
Here you
the
are
thread
considering.
IDs are starts from 0 to infinity.
Okay.
If the new block is created.
Okay. First of all, I'll tell you why we are creating new block, because as I told you, we have limitation on maximum number of threads per block, right? As of now, we are working on very small statement, so it is okay that we can have only one block. But as problem size increases, we have to go for multiple blocks, and according to that, we have to create number of threads. That is the first thing. Now coming to your point here, if you consider only thread idx.x, it will be always local, and we are not changing those ID. For example, I can store that value in an integer variable also. Let's say I will use tid as a variable where I'll store this thread ID value. Right. Let's say you want to retrieve block ID. I will use bid variable maybe, and I can store that value block ID. Likewise, you can retrieve the block dimension also. I'll use BDM. So I can use here block dim.x. So when you provide this thread configuration or block configuration, already when you call this function, 2 blocks and 5 threads are created, right? And all these 2 blocks and 5 threads will try to execute all these statements, right? Now let's say here we are having, let's say, 1 block and 5 threads. Now what will happen? 5 threads will be created and 5 threads will try to execute all these statements. Now what will happen? For thread 0, the thread idx.x value will be 0, right? For all threads, these 3 variables will be created, right? For all 5 threads, they will be having this independent copy of these all variables, tid, bid, and bdm, right? But for thread 0, this tid value will be 0. For thread 1, this tid value will be 1. For 2, it will be 2, and so on. For all threads, bid value will be 0, right? Now if I change it to 2, 5, now what will happen? We are launching 2 number of blocks, and every block is having 5 threads, right? Now we are totally launching 10 threads, and for all 10 threads, these local variables will be created, right? So 10 threads are there. So 10 copies of TID, 10 copies of DID, and 10 copies of BDM will be created. And obviously, for from 0th block, TID will be 0 and BID will be 0. So these variables can retrieve those values. So as per your requirement, you can retrieve in any variable any of these values: thread ID, block ID, or block dim.x, right? So these copies will be local to every thread. Now based on these values, we can create that formula, right? Now for thread 0, right? First zeroth thread from 0th block, TID will be 0, BID will be 0 and BDM will be 4. So I can create new variable global ID, that is GID, and that is nothing but this TID plus BID multiplied by BDM, right? So here again, this global ID variable will be created for all the threads, right? And every thread is having its unique copy of GID. And this GID value depends on thread ID, local thread ID, block ID, and block dimension from this. Fine. I hope that makes more sense now.
Yes, sir. Sir, can we say that it is like the list function? The list of the index value as common as starts from 0 for all the lists, but it have the unique variable names. So we access the elements, we can use the variable name with its index position. Am I correct, sir?
Exactly. Yes.
Okay, sir.
Yes.
Okay, sir.
Yes.
Thank you.
Sir, I had a doubt too.
Yes.
Hello?
Please.
Sir,
Yes.
I
Yes.
tried executing this code, but for some reason, in my code, block 2 is getting executed first.
No. As I told you, you cannot control which block will be executed first or which block next. What happens typically? You are saying you want to execute multiple threads in parallel, right? So all threads will start execution at the same time. Now you are printing on screen, right? You are executing in parallel and all threads are trying to print on the screen. But you are having only your screen is eligible or maybe capable to print one instruction at a time only, right? It cannot handle hundreds of threads at the same time. So your screen is IO device. So whichever thread completes its execution print statement first, and whichever thread puts that request in the queue first, that particular request will be printed first. Just give you a short idea what is happening in that. Just give me a second. Okay, so let's say you are having two threads, thread 0 and thread 1 in, let's say this is your block 0. Then I'm having another block 1 where I'll having thread 0 and thread 1, right? So these four threads will be executed parallelly. But in our computation, what we are doing, we are trying to print some value, right? And when we are saying print means one, we are displaying on your screen, right? You are displaying on your screen, and when all these threads will send the print request, those requests will be first of all placed into the queue, right? Your processes is parallel, your display device is not parallel, right? Your print statement, when you execute, all the requests will be given to operating system in queue, right? Maybe when you first execute, maybe it is possible that this thread completed first that print execution, and this thread will be keep its request into this queue first. Maybe next this one, next followed by this one, and followed by this one, right? So this is the scenario, and all the requests will be given in queue format, and it will print one by one, and you will get some kind of this kind of output. But it is possible that next time when you execute, other thread will go first, right? It is possible, quite possible that next time, rather than going this thread first, it is possible that a thread from this block will put request in the queue first, right? So execution is parallel, but we are having limitation on your display that which particular statement to be executed for, or maybe we have to print that in order, and that is the reason we are getting the output in some sequence. And maybe if you change that order, or if you execute multiple times, that order may get changed. Fine.
All right,
But
sir.
if you have some computations here, different computations like some ordinary operations, all threads will perform at the same time. computations in parallel, right? Because the display is having limitation of handling one request at a time. So that's why it is printing one statement at a time, right? And whichever complete first, it will be placed into the queue first. Fine?
Yes, sir, got it. Sir, but is there any way to make block 0 get executed first? Get printed
Why
first,
you
actually,
want to do that? No, why you want to do that?
for displaying? Because now I'm getting the iterations as 5, 4, 3, 2, 5, 6, 7, 8,
It
9,
is
and
okay.
then 0, 1, 2, 3, 4.
Look, if you want to follow in specific order, that means you are serializing that. You are saying that 0 will be printed first, then 1 will be printed next, then it is a serial application. The whole purpose of parallelization will be lost in that case, right?
Okay, sir, got it.
So we want to execute in parallel. Let it be whoever complete first will go into the queue first, right?
Okay, sir. Thank you, sir.
Yes. Again, there are some functions where maybe privilege is there. Let's say you want to in parallel code, let's say you want to serialize specific operation, that is also possible, right? But ultimately that is not whole purpose of parallel computing. In some unavoidable cases, maybe you want to serialize some specific tasks, then it is okay, you can go with that. But when you are using GPU or any parallel computing architecture, you want to execute in parallel, not in serial on that device. Fine.
Okay, sir. Sir, and one more doubt from one of the previous programs. Sir,
Yes,
the one with we had an if statement, and we had to check if the thread ID is this and block ID is this, then it would print the success word. That
exactly.
program. Sir,
Okay.
in that, whenever we execute the program, it executes all the threads, right? Which is why we had to
Yes,
remove the else statement. Sir, is there any way
exactly.
to execute only one particular thread?
Yes, you just mention here only one thread is there now. Rest of the threads, they don't have any work to do here.
Sir, but they get executed, right? That is why
Yeah,
we
you
had
are
to remove the else
creating the thread
statement.
means they'll be sitting idle. That will result to poor utilization. That means your programming strategy is poor itself, right? Obviously, it was a dummy code, so generally when you go with this one thread will do this task, other thread will do another task, or other threads will not doing to perform, then why you are going to launch? For example, you want to, let's say, uh, do a job only once and it is not parallelizable, then in that case you'll create only one thread or maybe whatever threads are required. Why would you go for maybe 256 thread blocks and 1024 threads per block, right?
All right, sir.
In case maybe let's say you have an application where some threads are supposed to do one specific job and other threads are supposed to do other job, right? Maybe odd indexed threads will perform one operation and even index another operation. Then in that case we can consider that half of the threads are working on different computation and half of the threads are working on some other computation. But only restricting to only one thread by launching millions of threads, it is not a good way to design your thread configuration, right? You have to again design configuration very optimally. What will happen? Let's say you launch 1000 threads and you are only doing useful job by only one thread, right? So it will lead to the poor utilization of your resources. We are asking 1000 GPU cores to execute, but out of which only one core you are utilizing, only one thread, right? That is not a good strategy to utilize.
Yes, sir.
More than 99% of resource will be unutilized in that case.
All right, sir. So,
Right?
but even for
Okay.
dummy code, what will be the function then? Just for
Uh,
one.
yeah, even it is dummy code. No, here it is dummy code. Deliberately, they have mentioned that this thread IDX equal to 1023 just to make sure that the participant will understand how this configuration works, right?
All right, sir.
If you want to, let's say, create only one thread, once you want to print, you just mention remove everything here, and you just create a function with this name, and you just mention the thread and block configuration as 1, 1. That's it,
All right, sir.
right?
Thank you, sir.
Okay. Okay. Okay, let me check any other messages there. Can we allocate two different unique program to block which is differ with its time of execution? That is also possible. Then both work in parallel or when both conditions are successful. Yes, according to you, maybe you are talking about a block. The threads inside a block will be performing different tasks, right? Ideally, it is not recommended on GPU computing. So where every thread is performing different tasks, right? GPU is most suitable for where you are having computations of type single instruction multiple data. So when I refer single instruction multiple data means, for example, if you refer this computation array addition, it is somewhere here. Yes. So if you see this computation, it is called as single instruction multiple data. So instruction is same for all the threads. There it is. We are having all the threads. So here, all the threads are having same instruction to execute, that is addition of two numbers. All threads are performing addition of two numbers, right? Only thing is different is that they are working on different data values, right? So thread 0 is working on index 0 of A and B. Thread 1 is working on index 1 of A and B. In this case, we have assigned same values for all the elements, but they are working on different elements of the array, right? So this type of computation is referred as single instruction multiple data. That means data is different, but all threads are working on the similar instruction, right? GPU is suitable for these kind of computation. But again, I'm not saying that GPU will fail to give performance if you have having different computations for different threads, right? For example, maybe you can have a program where you can say even index threads are going to perform addition and odd index threads are going to perform subtraction. That is also a dummy computation. Where you can say that half of the threads are working on addition, half of the threads are working on subtraction, right? Then you have to modify code. If thread ID is even, then perform addition, else perform subtraction, right? That way you have to modify. But if you have more and more number of if else statements, then again it will deteriorate your performance on the GPU side, right? So typically the strategy or maybe optimization thing is that never try to increase multiple if else statements in your kernel, right? Try to avoid these kind of you can say if else statements in your GPU function. Fine. Okay, now we have seen how to accelerate that program using your single block as well as multiple blocks. I guess here we tried to use multiple blocks as well, so 2 and 5, and we got how to use this thread IDX and block IDX, right? So that is your next topic, that is using multiple blocks, that we already covered, right? After session, maybe you go through all this text information that is mentioned. Again, the same thing they mentioned in the text format. If you want, you can practice by reading those paragraphs. Now, the last topic today's session is going to be this memory allocation to be accessed GPU and CPU, right? So this is kind of some intermediate or advanced topic memory related, okay? But again, earlier, if you go via the older versions of CUDA, where they have to explicitly allocate memory on CPU side and memory on GPU side. But now they proposed a new way of accessing memory where you don't have to work on CPU side memory separately and GPU side memory separately. So as I told you, your CPU is having its own memory. So let's say I'm having CPU and there is a GPU. So CPU and GPU both are having their own main memory, right? So whenever you want to compute any operation on GPU, first of all, let's say the data is initially present on CPU side, you have to transfer it to the GPU side, right? And that need to be performed manually by writing some explicit function, right? Once computations are done, then again you have to transfer data back to the CPU side because results are expected at the CPU side, right? So this is what we used to perform, I think before CUDA 6 or 7, right? Now latest CUDA version is around 11. So before that CUDA 6, the data transfer was explicit by using some function calls, right? But now in latest GPU, it is considered as unified memory. Meaning is that you just, as a programmer, you just allocate memory either on CPU or GPU side and you perform your operations. Automatically, these drivers will take care of to transfer data from CPU to GPU or GPU to CPU, right? So for example, let's say you allocated memory for a variable A on CPU side, but now you are doing computation on GPU side on the same variable. Then automatically data will be transferred from CPU to GPU, right? Next time, let's say you updated this variable A on GPU, and next time a CPU function you are executing, and that is will work on, let's say, executed on CPU. Now that A variable is present at GPU side, but CPU side you are referring, so automatically it will be transferred. That is called as unified memory in case of GPU. So here you don't have to worry about whether data is present on CPU side or GPU side. You just once allocate it and automatically it will be taken care by your underlying device drivers, right? So here it is called as CUDA malloc managed memory, right? So now A on GPU and CPU that can be used at any time. So typically in C programming, how we allocate memory? We declare one pointer and we allocate memory using malloc. And then after use, we remove or free that memory. Now, when you are writing CUDA program, you are going to allocate memory using this CUDA malloc managed, right? So that if you refer this A on CPU side also on GPU side, it will not throw any error. And you don't have to transfer the data manually from CPU side to GPU or GPU side to CPU. As a programmer, it is kind of a pool of both memories combined together. That means on bird's eye view or top view, you will consider this as the same memory. You don't have to worry. You just allocate it and you, as per your requirement, you will refer those memories. But for user point of view, it is a single memory, right? As a programmer point of view. And who will take care? Internally, automatically it will be taken care by your drivers, right? To transfer. Whenever it is required on CPU, if it is not present, bring from GPU to CPU. If you are referring GPU, it will be transferred from CPU to GPU, right? That is called as managed memory, CUDA malloc managed, right? So in typical C program, we use malloc function, but now when you are using CUDA programming, so you will be using CUDA malloc managed, right? And what is the syntax? You declare one pointer first, and you will pass here address as a first argument, and amount of memory that is required, that will be the size, right? So let's take a simple example here, exercise problem. I will just open this code. Here it is mentioned how we are going to allocate memory, right? So here we have to refactor. Oh, sorry, I'll explain the program first. So it is a main function. Inputs n size is 100. A pointer is declared A and size variable which is of size n into size of int, right? So 100 into size of int, this much amount of memory it is required, right? This is a C function where we are allocating memory using malloc function. We have to refactor so that it will be accessed from CPU and GPU as well, right? Then we are having a function init function which is taking input argument as that array A, and we are passing the size n, and init is going to initialize all the array elements to I, right? A of 0 equal to 0, A of 1 equal to 1, A of 2 equal to 2, and so on, right? And then once you complete that initialization, we are calling double elements function on GPU. How we can recognize it as GPU? Because you can see here brackets are there, right? Angular brackets. So that means this is a GPU function. here we will specify number of blocks equal to 10 and number of threads per block equal to 10. So 100 threads we are launching. Why 100? Because their input size is 100, right? Now we are passing a comma n variable, and then if you see this double element function is just taking the corresponding array element and it is multiplying by 2. So a of I equal to a of I multiplied by 2. This is the statement, right? And this is executed on GPU side, right? Once the computation is over, we are using CUDA device synchronize. That means we are asking CPU to wait till this GPU function completes. And after that, we are using check elements are doubled or not, a CPU function which is checking whether elements are doubled correctly or not, right? So it is the function which is checking whether your output is correct or not, right? It is checking whether a of I is not equal to I into 2, right? If it is satisfied, it will return false. If it not, it will return true, right? So this is a simple function where on every array element we are performing doubling. Now here what is asked, we have to refactor this code so that it will get executed on GPU as well as CPU. As of now, the memory is allocated on CPU side, but we are calling a GPU function, right? So here I'm having CPU memory and GPU memory is there. Now a variable is on CPU side if you use this malloc function. Now if you try to execute this double element function on GPU side this a variable is not there, right? Because you explicitly allocated on CPU side only, right? Now let's try to run what will happen, right? So it is giving output as false, right? Your whatever your results are there, those are not correct. Now we have to refactor it so that it will be executed on GPU side also. So I will just copy paste this CUDA malloc managed, right? Right. So this will allocate memory to this a variable of size here, right? Then let's execute it. True. It is showing code dumped error also. Perhaps we have to use here CUDA free, not free. I think CUDA free we have to use, right? Free function is for malloc and CUDA free function for CUDA malloc managed, right? So here we are using CUDA malloc managed, so we have to use CUDA free. And now if you execute it, you will get no error, right? Your elements are double true and there is no error. Fine. Okay, take few seconds, go through this program, observe it, what is happening. In case if you have any query, you can ask. Try to execute parallelly whatever changes I'm asking, you also attempt to do that. Okay, could you explain the function? Yeah, I'll get guess previous query first. I don't know pointers. I am Python programmer. Say it is in simple. Okay. For those who are Python programmers, here I'll try to just give you a simple example of a pointer. So in your, whenever you declare any variable, let's say there is a statement int a, right? Those who already know this pointer concept, they can start continue working on this execution configuration, try to play around with that code. Those Python users, I'll just give you a brief idea about what is pointer. So whenever you declare int a variable, right? So let's say int takes some amount of memory, let's say 4 bytes. So 4 bytes space will be allocated here, right, in main memory. So this is your main memory or RAM, right? So a will be allocated here. Now pointer is a concept where which can store address of another variable. So I can have, let's say, integer b. So this is the syntax to represent a pointer. So b is a pointer to an integer of type to a variable of type integer, right? So what is this b can store? B can store address of another variable of type integer, right? So I can write b equal to ampersand and of a. That means b is holding address of variable a, and in main memory for every variable there is a corresponding address is associated, right? Address in the sense location, right? So using that location only your CPU will be able to access those values, right? So b equal to address of a, that means b is a variable of type pointer which is going to store address of different other variables of type integer. Now using this b variable I can modify or access the values of a, right? If I want to modify, I'll just use a dereference variable b equal to, let's say, 9. So whatever value of initially a was there, I can modify it to 9. So using the address of that variable also we can modify, and pointer is a variable that is going to store the address of another variable, right? So in dynamic memory allocation, we use pointer concept here. So we'll create a pointer first of all. We will allocate memory using this malloc function. Sorry. We will allocate memory using this malloc function, and this a will store the address of this memory, right? So let's say now here size is n into size of integer. So 100 is your n, let's say, and integer takes 4 bytes, right? So it consumes or it requires 400 bytes of memory in your RAM. So 400 bytes of chunk will be stored in your allocated in your RAM, and its starting address will be returned by this function malloc function, and that will be stored into this variable a, right? Now variable a is holding the starting address of this chunk of size 400 byte, right? I know slightly tricky to understand this concept pointer, right? But I tried to just explain in very short manner what is pointer. That is holding an address of memory, right? Again, to understand this malloc and integer pointers and addressing, dereferencing, it may consume at least 1 hour to understand in detail, right? So that's why I tried to explain in very short manner. I hope that at least makes some sense now. Could you please explain the function CUDA malloc managed? So CUDA malloc managed, as I told you, in CPU side we are having its own RAM, and GPU side it's having own RAM, right? If you use this malloc function, memory gets allocated only on CPU side, right? And now if you want to execute any function and if you want to work on this array A, that is not present on GPU side, so it will throw error or maybe some garbage value, right? If you work on this a variable that is on CPU side, if you use malloc function. If you use CUDA malloc function, right? Now if you are executing any function on GPU and you are referring this a, if it is not present, automatically it will be transferred from CPU memory to GPU memory, right? It will not throw error. It will first transfer data from CPU memory to GPU memory. It will perform computation, and then let's say next time again you are referring the same array A that is modified at GPU, and now you are referring at CPU side, then automatically it will be transferred first from GPU to CPU, and then you will work on this, right? As of now, even if you're not getting clear picture of this CUDA malloc managed, don't worry, because the next chapter is totally dedicated for this CUDA malloc managed, that is called as unified memory, right? So don't worry, I just gave you brief idea about what is CUDA malloc managed here. Just remember that it won't throw error if you try to refer the data that is not present on CPU side, right, or GPU side. It will execute by transferring the data. Fine. Okay. Now, next topic is again a very simple topic. What to do when there is a mismatch between grid size. Okay. We execute it. Okay. Now, in previous case, we have seen data size was exactly equal to number of threads, or we launched number of threads equal to exact size of your data. So size of data was 8 and we launched 8 number of threads. But what if we are having only 5 data points and your thread configuration is 2,4, right? What will happen in this case now? Definitely using your global ID, you will be mapping every thread to a data point. But what about this remaining 3 threads? Right? What about this remaining 3 threads? What will happen? The thread number 1 here, it will try to access data of 5. This will try to access data of 6, and this thread 3 will try to access data of 7. But we have not allocated memory for these data points. So in that case, it will throw runtime error, or it will tell you invalid memory access, because data is only having 5 elements and you are trying to access 6th, 7th and 8th element, just because your configuration is like this, right? So how we can handle this? Just by using simple condition that if data index or your global ID is less than n or not, right? So if we can put one condition in the configuration itself, double element, right? So in this program here, we are mentioning if I is less than n or not, right? So that means if let's say we have launched, let's say number of threads equal to, I will launch number of threads for a block equal to 20. So here we are launching 200 number of threads, right? But how many threads actually we need? Only 100 threads. Why? Because input size is 100, so 100 threads are enough. But by mistake, let's say I launch 200 threads. Now what will happen? All 200 threads will get their corresponding global ID, and if I don't mention this if condition, then what will happen? It will work very well for first 100 threads. They will try to double the every element. But what about next 100 elements, 100 threads? They will try to access a of 101, right? But we allocated memory for only 100 elements, right, here, and we are trying to access 101th element to a of 199. For this, we don't have memory allocated to this, and thread number 100 to 199 will try to access these elements because we launched 200 threads, right? So in that case, it will be invalid memory access, right? It will throw an error and your program will suffer from your invalid memory access or runtime error, right? Let's try to execute and check whether it is it will throw error or not. These are runtime errors. Sometimes it will throw error or sometimes it won't. Right, so here you can see it is not throwing error, right, though we have created launched these 200 threads, right? But in reality, these kind of errors are very difficult to debug, because while compilation also you will not get error, and while your execution also you have not encountered with any error, right? But always you have to make sure that you are not going to refer a data element out of bound, right? So always, to ensure that what is your data size, always ensure that your number of threads I, right? A thread ID must be less than number of elements, right? For only those threads will be having this computation, and rest of the threads, there's a number from 100 to 199, they will not perform any computation, right? So this is how we have to ensure that out of bound access, right? It is possible out of bound because every time we will not get the configuration of threads exactly with your number of data elements, right? For example, if let's say I'm having 9 number of data points are there, right? N equal to 9, right? But I mentioned that my thread block size equal to 4. Now, how many blocks you will launch here to work on the 9 data points? How many thread blocks you will launch? If you want to work on 9 elements and your thread block size equal to 4, how many blocks you need to work on these 9 elements? How many total number of threads are required to work on 9 number of data points? How many threads are required? We need 9 threads, right? And we have thread block size equal to 4. So if I take one more thread block, then number of threads will be 8, right? But the number of thread block size is 4, and if I take 2 thread blocks, only 8 threads will be there, but we want 9 threads. So I'll create one more thread block and total number of threads will be 12, right? But out of which only 9 threads are supposed to perform work, rest of the 3 threads will be sitting idle. We will not assign any task to them. So 3 thread blocks we are going to launch. So in this case, with this thread block size, we will not get exact number of threads as like your data points. So in that case, sometimes you'll be having more number of threads as required, right? So that is called as grid size work mismatch, right? Grid size work mismatch. Fine. So in that case, we have to always ensure that whatever your ID is generated, we have to ensure that it is supposed to be less than n, and then only we'll allow to perform the work that is inside this block. Otherwise, we'll not allow to enter into this computation. This will save your headache to find out the error, right? Because this is not compilation error or runtime error. Sometimes runtime during some environment it will throw error, but in some environment it may not throw error. Just like here, though I created 200 number of threads, still it is not throwing error in this environment, right? But always make sure to launch. Make sure to use that if statement so that only the required number of threads will perform the operation. That is one thing. Now, what if we are having less number of threads than desired, right? For example, let's say here we have let's say we are having same vector addition kernel, right? And we use GID equal to that global ID. And if that GID is less than n, only when we are going to perform the computation, that is fine. But what if, let's say, we are having number of threads less than n, right? Let's say there are 8 number of data points are there, and we have only 4 number of threads, right? So what we have to do, if you use the normal strategy, then thread 0 will perform addition of 0th element, thread 1 will perform addition of first element, second element, third element, right? Here we are having less number of threads and more number of data points, right? In that case, what we can do, we can assign thread 0 first, to perform all these corresponding works based on their thread IDs. Next thing is we can assign the same thread 0 to perform work on this element. Thread 1 will perform on this element, 2 on this, and 3 on this element. Meaning is that we are having limited number of threads and data size is more. Right? In that case, we have to allocate more work per thread. Right? If we have less number of thread, that is fine. Here we have seen normal scenario. Every block is going to perform corresponding work, right? Likewise, but if number of threads less than total size, in that case, first of all, we will assign 0th thread will perform 0th element, first thread will first element, second, third. Next time, 0th element will perform, 0th thread will perform 4th element, first thread will perform 5th element, second will perform on 6th, and third will perform on 7th. Right? So this is how we have to decide the work. But how we can perform that? Using the stride size. Right? How stride size we can have here? First of all, we'll calculate how many threads are there in total that we are going to launch. How many threads are there? Here 4. Right? So we'll calculate total number of threads into block dimension.x multiplied by grid dimension.x. Block dim.x means block size, and grid dim.x means total number of blocks. Right? So total number of threads we can calculate using block dim.x multiplied by grid dim.x. Right? Number of blocks multiplied by size of each block or number of threads per block. So you'll get that stride. Right? So first of all, every thread will perform computation on corresponding elements. So thread 0 will perform 0th element, 1 mean 1, 2 on 2, 3 on 3. Next time, if you see the 0th thread is supposed to work on the 4th element. Right? And how will calculate this jump from 0th to 4th element? That is called as stride. And how we can calculate this stride? Just we have to calculate total number of threads. Right? We calculated this total number of threads, and once the thread 0 complete this operation of A of 0 plus B of 0, it will go and jump on the next computation, that is A of 4 plus B of 4. Right? So from 0 to 4, how it reached? Based on number of threads. How many threads are there? 4 threads. So that is the stride. And how we are going to calculate this stride? Using this block dim.x multiplied by grid dim.x. Right? And same way, every thread will, if we add 4 into that, the next job will be there. So if I add 1 plus 4, that will be 5. So next iteration, thread 1 will perform on fifth element. Right? Next, if you take 2, it will work on the next 2 plus 4, that is 6th element, and so on. Right? So likewise, it will perform. Right? So this is when, if you are having less number of threads and more data. Right? So again, you have a presentation here to do that explain the same thing with this Jupyter notebook. Right? So here you can see we are having 8 number of threads are there, but total work is 32. Right? 32 elements are there. So initially, first 8 threads will perform work on first 8 elements. Then thread 0 will perform on which element it will perform? Can anyone tell me now? Now 8 threads perform the task on first 8 elements. Now next iteration, thread 0 will perform on which data point? Exactly. And how we'll calculate this 8 value? Based on number of threads. Right? How many threads we are having? 8 number of threads. How we can calculate? Number of blocks multiplied by threads per block. Right? This is 2 into 4. Right? So once you get that 8, now thread 0 will perform on 8th element. Next iteration. Right? Next iteration 16. Next iteration 24. Similarly, thread 1 will perform next iteration 1, then 17, then 25, and so on. Right? So here, even though we are having less number of threads with us, still we can work on the data size, which is way bigger than number of threads, right? As I told you, I think in the previous session, someone was asking, what if we are having data sets which is more than available number of threads, right? So in this case, we have to decide first of all what will be the number of threads first. We'll allocate corresponding tasks, and then where will be remaining tasks will be again divided among the same number of threads, right? So this is how it works in case of strided loops. Exactly, it is 2 into 4. Fine. Now again you will see the similar assignments will be there that you have to work on grid strided loop. So you can open any this program grid double.cu. So what is expected here in the current application, n is larger than grid. Refactor this kernel to use grid strided loop in order to order that each parallel thread work one or more than one element of the array, right? That is what. So now here we are having this particular global ID, and here input size is 10,000, and according to them, the we are having threads per block equal to 256 and number of blocks equal to 32. So total number of threads we are having is 8192, but total number of elements equal to 10,000. So how we can modify this? First of all, we have to calculate the stride. So I will write stride equal to, what will be the formula for stride? Stride in the sense total number of threads we are going to calculate. How we can calculate it? No, thread. Okay. Instead of thread dim, I think you have to use grid dim, right? Grid. Yes. Dim dot x multiplied by block dim dot x. This will give you total number of threads that is launched in this function, because you know number of threads and number of blocks per number of threads per block here, right? But you don't know inside this function that configuration. So for that we are having block dim.x, that block idx, all these parameters. Based on that we can calculate, right? Now we got stride here. We simply need to do one thing now, to use the for loop, right? For I will use integer I equal to, sorry, I will use different name here. I will use gid here, gid global id, and then I equal to gid I less than n value and I plus equal to stride, right? And we just have to put this into the for loop. That's it, right? Now what is happening? Initially, when I equal to gid, all the 8192 threads will work on corresponding 8192 array elements. Next time, you tell me when thread 0 will work on which element based on this configuration. Thread 0 will first of all double the element of a of 0, right? Next, which value it will try to double? Thread 0. Think on it. You refer this one, right? Here you said that thread 0 will work on data element 0. After that it will work on 8, right? Thread 0 work on 0, then 8. Now my question with this example, thread 0 will work on a of 0 now. In the next time, on which data point it will work? A of what? Any more answers? Yes, try it. Whether it is wrong or right, that is another issue. I'll give you again one reference here. So you are referring thread 0. It tried to update on 0th element first. Then it is incremented by stride. What is stride? Block dim.x multiplied by green dim.x. It will be 8 here, right? So that's why thread 0 next time it is working on 8. In the same scenario here, initially thread 0 is working on a of 0. In next iteration, when I equal to I plus stride, it will work on exactly 8192, right? So likewise, it will increase the stride. Fine. So let's say whether it will work or not. Any other thing they asked? No. Yes, it is giving correct answer. Fine. Okay. So with this, we can consider our first chapter is over. Now there are some basic error handling and all this stuff is there, so you can read that and you can use. That is not specific to your CUDA programming and writing parallel computing. This is a error handling techniques, right? So this is common to in C program also that you can refer, right? One more thing is at the end of this particular chapter there is an exercise there, so you work on it. What is expected from that assignment, you work on it. If you stuck somewhere, there is also solution provided here, right? You consider this as an homework and you can work on it. And there are some advanced contents are there, like 2-dimensional and 3-dimensional you can say thread and block organization. That is common again for your Python users and your C++ users. I'll explain this 2 and 3-dimensional behavior or organization of threads when we start with the Python course, right? Once you complete that, again, if you want to explore further how it is organized, you can explore that also, because this is a Codathon event. So you have freedom to explore all the topics, or have freedom to complete all the courses, right? Without waiting for me to explain everything, because all the topics are self-explanatory and all the information is given here. So if you want, feel free to explore all the chapters. Feel free to work on all the assignments also, right? It is good if you complete maybe before the deadline, right? If you complete, you'll get enough time to revise, practice, and work, maybe get ready for the next coding round, right? Fine. So there are some advanced topics are there that we'll try to cover when we discuss about Python programming. Okay. Tomorrow at 9:30 we will start the session, because today we lost almost a couple of hours in inauguration and everything. That's why we are a bit lagging. Tomorrow we'll start at 9:30, and we will start with the next chapter, that is memory management. Again, very interesting topic. And the next two chapters chapters are quite small compared to this first chapter. By tomorrow, at the end, we'll try to finish this CUDA certification. Okay, fine. So if you have any doubt, you can ask. I'll be here for 2-3 more minutes. Again, those who are facing maybe trouble in understanding the concept, don't worry. You'll be having enough time tonight also to grasp all those things. Even if you are not able to understand any specific topic, you just drop me a message in a WhatsApp. I'll try to explain it, right? Or maybe the next session, early morning session, I'll take some queries, and for 5 to 10 minutes, I'll explain all those doubts, right? Don't get discouraged because this technology is new, so we are also not expecting you to develop very big kind of application. Even your coding round is also, we have designed the problem statements where you can work based on your 3 to 5 days training only. So the coding round is not very difficult, or maybe the problem statement are not with very which require very high level concepts in CUDA programming. Whatever you learn throughout this course, what is mentioned in your certification chapters, that is going to be enough to complete those assignments, right? So even though some of you, if you are feeling some maybe problem in understanding all those concepts, give it some time, right? Tonight you again sit with your team, you go through all the course contents, right? You read one by one and practice by modifying the code. Then and then only you'll be able to understand all the concepts. Fine. Okay, so with this we will conclude for today's session. If you have any questions, you can ask. I'll be here for a few more minutes. And make sure to join all the sessions on time, because every session, if you are losing 5 minutes, then almost will be losing 15 to 20 minutes. And within 15 to 20 minutes, we can complete one topic, right? So make sure try to attend all the sessions on time. Okay. If you have joined this offline mode, it will be sitting in one hall only day and night. I have attended, I have mentored few national level or international level hackathons where they used to sit for whole day and night in the same hotel and in the same hall itself. We used to sit in one hall itself, right? The everything sitting arrangement, dinner arrangement, lunch arrangement, sleeping arrangement also made in the same nearby you can say rooms. And we used to work for 24 hours anytime. We used to sleep maybe for 6 hours, right? So assume it is happening it as like offline event, and take it seriously and try to continuously work. Maybe let's say uh, for 3-4 hours one of your team member is working, next 3-4 hours other team member is going to work on the different segment. So accordingly you have to divide your problem statements also, right? Accordingly you have to divide your task also, so that collaboratively you can work together and try to solve the problem statements. The question is content in the CUDA with C and Python are same, almost same, syntactically different. The programming strategy is slightly simpler in case of Python programming, right? So in C++ programming, explicitly you have to do all the stuff. In Python, there is some automatic, you can say, parallelization is also present. But again, automated parallelization is not encouraged for computation. But compared to C++, programming in Python is slightly easy. I'm just telling slightly, but to solve assignment problems, we have to write explicit code. So it is better if you understand the concept from C++ as well. Fine. Any other doubt before we conclude today's session? Actually, we tried for offline event only, but unfortunately, everybody is scared of this COVID situation, and this is a national level event, and every part of the country from participants from every part of the country are joining, and they'll be traveling through different modes, and that is quite risky to ask everyone and to gather into the same hall, right? Because of that, our management also was thinking that why you are risking there, because the disease is quite very dangerous. So that is the reason. Otherwise, we would have enjoyed this kind of events in offline mode. But in future, in the next semester, we are also planning similar event, but that is for your AI, artificial intelligence codecathon. That is not parallel computing. But definitely we'll try to do that kind of event in offline mode. Are other colleges having offline event, or it is just like I'm not getting your question. Are other colleges having offline event? Perhaps maybe they are having an offline event. That is okay.
Maybe, sir.
No,
am I audible?
yes. Yes.
Just to the internal participant, can you raise hand if like how many people, if you are like in the campus currently or nearby area, you can come. Then we can
expect
request
30 to 40.
Okay. Maybe, sir, for them anyway you are taking, sir, so they can come in blended.
But that we have to reserve these halls at least 15 days prior. right? As we cancelled
yeah.
that